Assalamu alaikum guys. Today I'll be demonstrating this equipment. The name of the equipment, as you can see here, is written here, boiling heat transfer unit. So what is the purpose of this unit? We will be using this unit to basically see the different boiling regimes. As many of you might not have heard about the boiling regimes, what are the boiling regimes? Basically, boiling regimes are introduced when we are boiling a liquid, and the boiling happens at a certain temperature depending upon the pressure. So for instance, we talk about standard atmospheric pressure. So when we are at standard atmospheric pressure for water, the boiling temperature would be 100 Celsius, or in some northern areas also it will be about 98 or 99 Celsius. But coming to the point, what are the boiling regimes? Boiling regimes are introduced when there is a difference between the temperature of a boiling liquid and the boiling surface. Boiling or heat transferring surface or heat providing surface, whatever you want to call it. When basically what happens when the temperature of the boiling surface or the surface in which the heat is coming into the liquid is higher. Definitely it has to be higher, so that is why the temperature will the heat will shift from the from the surface to the liquid. The temperature has to be higher. The temperature of that surface has to be higher. So how much higher? That is the question. If the temperature is, let's say, 5 degrees higher, so there is basically we call it conventional boiling, or let's say it is a type of boiling in which the heat transfer happens or uses only the mode of transfer for heat is only convection. So that is only conventional boiling. And the second type of boiling is when the temperature difference is higher than 5 degrees. When the temperature is higher than 5 degrees, then then there is another type of boiling in which some little vapors or bubbles start to appear. When the bubbles start to appear, the type of boiling changes. Now we call it nucleate boiling. Nucleate boiling, in that nucleate boiling, in the start of a nucleate boiling, the bubbles start to appear, and after some time, for some time, those bubbles grow up and start to leave the heating surface. So, and those bubbles go into the liquid, and that liquid and they pop into the liquid or at the surface, depending upon that how much they have to travel and what is the temperature difference. And then continuous bubbles are produced, and that is complete nucleate boiling. Then there is transition boiling, and then the last type, the fourth type, which we will not be discussing here. Now coming to the apparatus. This apparatus has the main parts of the most important part of the apparatus is this cylinder, in which we have a refrigerant. You can see the refrigerant is present in here. We have to maintain a certain level of the refrigerant. We are going to boil this refrigerant and see the effects of the boiling on this refrigerant. So which one is it is basically R141B. You can search it out. You will find its specifications. You will find out that its standard boiling temperature is about 32 degrees Celsius. So we don't really call it a liquid, we usually call it a gas, but now it is in the liquid form at this temperature. Coming to the parts of this apparatus. Now, what is the main? It is the main cylinder. The main cylinder is basically it is made of glass, and inside it you can see that there is a coil. This coil is called condensating coil. In the experiment, we will be using it to condensate the vapors of refrigerant. Basically, it is the second part of the experiment. We will discuss it later. Now, coming to the parts again, this is the pressure gauge. We can measure the pressure of this cylinder, and there are basically sensors, temperature sensors. Now what are these temperature sensors? First of all, this is, you can read out the tag, water temperature, water out temperature. So when we are using this coil to condensate the vapors, we will be using this temperature as well. We will be taking a reading of this well, and there is another tag over here. You can see this is vapor refrigerant temperature. So what are the what is the temperature of the refrigerant? We will be noting, this sensor will be noting that temperature. Now there is another sensor which is liquid refrigerant temperature. Now the basically you can see, you will see basically that in this cylinder the refrigerant is present in two states while boiling. First, one in the vapor form and second in liquid form. They both will have different temperatures. Some guy, you might be thinking that how is it possible that the vapor temperature is different from the mother or refrigerant temperature, mother liquid or refrigerant temperature. Yes, it is possible that these two temperatures will be different. Now coming to the panel of this equipment, you can see that there will be different readings that you can take from here: liquid refrigerant temperature, vapor refrigerant temperature, then water in temperature, water out temperature. After that, heater voltage, heater current, and heater surface temperature. Now, and then there is heater regulator and main switch, heater switch. Heater switch, you can turn off heater from here, turn on or off the heater, and then there is a heater selector. I'll tell you the purpose of the heater selector later on. Now, where is the heater located? Basically, inside this refrigerant, you can see this bar, which is colored as yellow right now, but it is made of stainless steel. Now, this is the boiling surface. This is the boiling, this bar that you can see. It has a different dimensions at the bottom, and the upper part has a different dimension. Basically, the lower part has a dimension of, I think, 30 mm in dia and 30 mm in height, while the upper part has a 15 millimeter of dia while 89 millimeters of height. So we will be using these dimensions to basically calculate the heat flux. Now, what heat flux? I don't think that I need to explain the heat flux. Now coming here is a rotameter. You can see this is a rotameter that will be used to see the value of what. It will be used to note the value of water in, how much water is going inside the inside this coil. So we will be using this one. It gives us the value in two units. One is GPM and other is LPM. GPM stands for gallons per minute and LPM stands for liters per minute. Now this is the valve. You have to control the water inflow from this valve. You can close it, you can open it. So this basically its name is written on the back side. You probably won't be able to see it, but I'm trying to show you guys the full name, flow control valve. So these are the main parts of this equipment. Now if you have to we can start the equipment from here. Just we have to switch it on. Now when we switch it on, you can see the values of temperatures, different temperatures: water in temperature, water out, liquid refrigerant temperature. Well, there will be a slight variation, but right now there is no water inside it, so it is not giving us the value of water. It is we are not feeding it any water right now, so it is air temperature, nothing more. Right now the heater is turned off. You can see the heater is off, so there is no heater voltage, no heater current. Now coming to the heater selector. Now basically these are you can say that these are two modes of heater. Right now it is 0, but at 1 and 2 more heat is supplied. Approximately double the power is supplied in as compared to 1 in second mode. So this is the purpose of on this switch, on nothing more. That it will only double the power, approximately double the power, not exactly double the power. And what is the capacity of this heater? It can provide up to 300 watts of power. And now let's start seeing the function. Let's see the function, how it operates. Heater switch, let's turn it on. Right now even you can see there is no voltage, no current, but we have to select the heater, that which mode we are going to use. Let's say we are going to use 1. Now you can see that there is some voltage 26, heater current is 5.4, 5.3. Now the temperature will start to increase as well. You guys will see that shortly. Now what can we do here? What is the purpose of heater regulator? Heater regulator is basically used to vary the heater current and the heater voltage within that same mode. You can do it with more accuracy, you can think of. Let's start the regulator, and right now the heater surface temperature is going out of control. We should, I think, control it. I think we should control it, yes, we should, rather than going berserk. Right now you can see this is the conventional heating mode. Right now basically you are not seeing, you should be seeing actually which one mode? Nuclear mode. But right now you are not seeing that because the refrigerant temperature is not on the boiling point. You would have been seeing that one, but right now it is not there. So I am using currently this mode. I have lowered the voltage and the current so that the refrigerant temperature, which is basically right now, you can see the value, liquid refrigerant temperature is right now 27, not at 32. When it reaches 32 or higher, then it will start boiling. So we will have to wait a little bit. Rather than waiting, I think I should speed it up so that you guys can speed it up and take the temperature. You guys won't be able to wait that much. That is why I'm speeding it up. Otherwise, these processes has to be steady. Right now it's not steady. It's not going to be steady. It is going to be an abrupt change process. So I think we can switch it to the second mode. Should we? No. Yes. Now you can see in second mode, I have switched it to the second mode, and the current and the voltage value has increased dramatically. So right now I'm just trying to increase, trying to get the refrigerant. Now, sorry. Well, yes, you can see the continuous boiling, but still the temperature. Now what is happening here? The temperature of the liquid is not at that, not at 32 or the boiling point, but still the boiling is happening. Why the boiling is happening? Because our heating surface is at 80 heating surface temperature is actually lower. Okay, is at 56 degrees Celsius, and 57 it is continuously rising. It is I think 25 degrees, no sorry, yes, 25 degrees above the boiling point. And the liquid refrigerant temperature is increasing. When it will increase to 32, I'll decrease the heater input. Now it has increased. Now I'll decrease the heat. I'll bring it to 1. basically I want to show you guys the first mode of the boiling. First of the mode of the boiling in which the heat transfer occurs only with, this is called as by the way it is called natural boiling. You can yes, it is the first regime. Yes, now we will come to first regime when the temperature drops to about 40 degrees or less than 40 degrees. So we will see that as well after some time. Now you can see that the refrigerant temperature is still increasing. And let's decrease it a little bit more so that I can show you the first mode of the boiling. In the first mode of the boiling, you can see the currents of the liquid while there are no bubbles present in the liquid at that time. Right now you guys might be wondering that why the temperature of the fluid is going above the boiling point. Yes, it is a closed cylinder. The pressure inside it is increasing as well. So you guys can note the value of pressure that is also going up. If you guys want to keep the value of the pressure, let's say at a constant, so you will have to use the water inlet, which I am not using right now because I am only demonstrating. We are not going to take any readings. Right now the temperature is dropping, but it is not that fast. You will see the first mode when there are no bubbles, when the difference between these two is 5 degrees or less than 5 degrees. So you guys have to wait a little bit longer for that. Basically it shot up. Right now the temperature difference is about 10 degrees and it is decreasing. I'll decrease it faster. Right now, even at this temperature, you can still see there are bubbles rising. If I think I can show you clearly, there are still some bubbles rising from the liquid. This is basically nucleate boiling, the second regime of the boiling, not the first one. In the first one, you will only see some currents of the liquid, which I might not be able to show because I have a lower image quality right now. So I think you guys can even see that if you boil the water at your own home. that the water currents start to develop when the boiling starts. So now coming to our main experiment. Now what are we going to perform, how we are going to take the readings. Now I have the manual with me, and I'll show you the table that you guys will have to fill out for this experiment. And this is the table, this one is the table. In this table you guys can see that you guys need heater surface temperature, the liquid refrigerant temperature, it is calling that T1, the difference of the temperatures. The difference of the temperature, a heater input, heater heat input, heat flux, and the last one is surface heat transfer coefficient. And basically we are here to find this surface heat transfer coefficient. What is surface heat transfer coefficient? You guys can find it out. I don't think that I need to explain it. Now coming to this experiment, we will set our experiment in the nuclear mode when there are bubbles being continuously produced from the surface of the heater or the heating surface. At that point, at some point, let's say that we set our inputs to 100 watts or above. Okay, 100 watts, maybe you can set for 100 watts you will have to put the heater, go higher, higher, higher and higher. Right now it is at about how much watts? 80. Right now it's at 80 watts. Now it is approximately at 100 watt. Approximately at 100 watt right now. So we can calculate the watts by multiplying these two parameters, voltage and heater current, and we can see that the boiling is happening here. We will wait for some time to take out our readings. To take our readings, what will we do? We will wait here and wait that this temperature becomes stable, liquid refrigerant temperature, and let's say the other temperature is vapor refrigerant temperature. So these two temperatures, when they become stable, their value is not varying that much. At that time we will do what? We will take these readings. We will note down the readings of heater surface temperature. Then at that point we will note down the liquid temperature. Then we will calculate delta T. Delta T is basically the differences of these two temperatures. While yes, there is one thing else, another thing now that we are taking the temperature differences, so we don't need to differentiate between the Kelvin scale and the Celsius scale. This is one of the, if you guys want to take the reading in Kelvin or Celsius, that is up to you. Right now the temperature of the refrigerant is still going up, so we will wait for that, and we will take out these readings. When it becomes stable, then we will change the input heater input again, and again take the value, and we will repeat it at least 5 times. And after that, to perform the calculations from this table, we have a heater input. Yes, we have noted that against the temperatures. Heat flux can be calculated by dividing heat input with the area of the heating surface. Right now, area of the heating surface, how can we find out the area of the heating surface? Area of the heating surface can be found out very, very easily by using the dimensions of the heating surface that I have described before. If you remember, I'll recall it again, that this surface has the dimension of 30 millimeters at the bottom, 30 millimeters in diameter and 30 millimeters in height as well. And the cylinder part, the thinner part, has a diameter of 15 millimeter, while it has a height of how much? 89 millimeters. So you can calculate the area of this surface easily by using geometric formulas. And the last part that you will have to calculate is the surface heat transfer coefficient itself, which is basically heat flux divided by delta T. Now you can easily calculate this heat transfer coefficient, that how much heat is this surface transferring. Now even if you see this these units of heat transfer coefficient, you can roughly tell that what does it mean. But still I would say that you guys search it out by yourself, and I think that is enough for this experiment. The questions will be dealt in the meeting.